So our we'll discuss our next topic, that is psychrometry. Is one of the most important topic that everyone should know. So first of all, what is psychrometry? What is psychrometry? So psychrometry basically psychrometry, is it visible? The screen is visible to you?
Yes, sir.
Yes, sir.
Okay. Psychrometry is the study of thermodynamic properties of water, of air, water vapor mixture. Water vapor mixture. So naturally in an atmosphere, you have combination of dry air and water vapor. So for the dry air and water vapor, the thermodynamic properties are very important. It should be known, because if we know these properties, then only you can utilize these things for design of systems such as air conditioning equipment for storage of fresh products, dryer for drying of cereal grains, and cooling towers in food processing plants. Okay, so that's why psychrometry is a very important term. For refrigeration and air conditioning problems, or if you need to some design, if you need to design some dryer, some storage equipment, then this psychrometry, knowledge of psychrometry is very important. So psychrometry is the study of thermodynamic properties of air water vapor mixture. Okay, so this is basically psychrometry. What are the different parameters? So there are various parameters definitely. So why this is psychrometry is important? This is very important. As I have said, in design of systems such as air conditioning equipment, uh, for storage of fresh products, fresh produce like fruits and vegetables, and dryers for drying of cereal grains, and cooling towers in food processing plants. So various terminologies in psychrometry. Obviously, it is a study of thermodynamic property. So there are various terminologies uh, that should be known for studying or for utilizing these properties. So what are those properties? We will discuss one by one. First of all, dry air. First term is dry air. So what is dry air? Dry air is basically the dry air. The dry air comprises of constituent gases of atmospheric air, constituent gases of atmospheric air, excluding the water vapor. Okay, so in the atmosphere, if you see, in the atmosphere there are various components. So the dry air comprises of constituent gases of atmospheric air, excluding the water vapor. Okay, so because in the atmosphere there are various gases, for example, nitrogen, oxygen, these are the major gases. Okay, nitrogen, oxygen, carbon dioxide. So nitrogen, oxygens are the major gases present in the atmosphere. So plus some amount of water vapor also present in the atmosphere. So dry air is basically comprises of constituent gases of atmospheric air. So whatever gases are there, they are basically considered dry air, but excluding water vapor. Okay, so suppose there is a system. There is a system. In the system there is, for example, you have gases, and then you have water vapor, so if you are considering only this gas, if you are considering only this gas, excluding this water vapor, in that case it will be dry air. That means in dry air there will be, when we are defining dry air, it is basically a composition of constituent gases of atmospheric air, but we are excluding the water vapor. So dry air comprises of constituent gases of atmospheric air, excluding the water vapor. There will be, so when we will define dry air, that means a dry air, only the gases, no water vapor. Okay, so second term is that we are going to discuss. Second term is moist air. Moist air. Moist air. So moist air means in dry air we have defined that it is a it comprises of constituent gases of atmospheric air. So in moist air means it is a mixture of dry air and water vapor. Okay, so this is about moisture. Dry air means only dry air, no water vapor. And moisture means this whole system, gases plus water vapor, this all together is known as moist air. But if you are considering only gases, excluding the water vapor, in that case it will be dry air. Is it clear?
Yes, sir.
Okay, next is saturated air. Next is saturated air. Saturated air. Saturated air means, so before we define this, let me, what do you mean by saturated air? Suppose there is a room. There is a room. Okay. So in the room, suppose there is air, there is moist air. For the moist air, there is some partial, because in the air, it is a combination of dry air plus water vapor. So for the water vapor, there is some particular pressure. There is some particular pressure. So if there is some particular pressure, so in normal condition, it will be normal moist air. But if you have saturated air, that means maximum amount of water vapor that can be possible for the dry air to hold, it is already there. So that means it will be saturated. So the saturated air is the moist air in which the partial pressure of the water vapor equals the saturation pressure of steam corresponding to the temperature of air. So for example, in normal conditions, suppose you have a dry air, in which you have 50%. You have 50%, for example, you have 50%, you have 50% water vapor. So this is normal condition. But if it is saturated air, in that case it will be 100%. In that case, your moisture content will be 100%. Okay, it will be fully saturated. The amount of water vapor will be 100%. So the definition we can write: the saturated air is the moist air. Saturated air is the moist air in which partial pressure of water vapor water vapor equals the saturation pressure of steam corresponding to the temperature of air. Corresponding to the temperature of air. Okay, we can also write the definition as, or it is a mixture of dry air and water vapor when the air has diffused maximum amount of water vapor in it. Okay, so that means what is saturated air? Saturated air is the moist air in which partial pressure of water vapor equals the saturation pressure of steam corresponding to the temperature of air. Or you can say it is a mixture of dry air and water vapor when the air has diffused maximum amount of water vapor in it. Okay, 18 I have written, this will be in it. Okay, so that means suppose there is a room, in the room there is particular water vapor, right? So yeah, for example, you have 50% water vapor in the air. So if you tell that you want to make it saturated air, so in that case, the maximum amount of water vapor that can be written by the dry air, you have reached up to that condition. So then it will be known as saturated air. Okay, so it is the mixture of dry air and water vapor, or moist air, rather you can say, when the air has diffused maximum amount of water vapor in it. So in a particular moist air, if you have maximum water vapor, in that case it will be known as saturated air. So in normal condition we don't have saturated, we need to make it saturated. So suppose we have a normal temperature, if you reduce the temperature after reaching a certain temperature known as dew point temperature, what happens? The air becomes saturated. So for making any air or any moist air uh, to saturate, or for saturated, for making any moist air saturated, we need to reduce the temperature of air water vapor mixture up to dew point temperature. So after reaching the dew point temperature, uh, it is converted to saturated air. So you will have the maximum amount of water vapor in the moist air. So saturated air means it is a moist air in which you will have maximum amount of water vapor. Rather, you can say the saturated air is the moist air in which partial pressure of water vapor equals the saturation pressure of steam. Okay, so saturation pressure of steam means it is the highest pressure. So when the partial pressure of water vapor of any moist air equals, they are equal. In that case, and corresponding to the temperature of air, in that case, it is known as saturated air. Is it clear?
Yes, sir.
Yes, sir.
Next is water vapor. The water vapor is the water vapor the water vapor presence in air known as moisture, and its quantity in air is important in all unit operation of food engineering, in all unit operations of food engineering. Okay, so the water vapor presence in air is known as moisture, and its quantity in air is important in all unit operation of food engineering. Okay, so water vapor means amount of water vapor present, because in the normal air, if you take any normal air of the atmosphere, which is moist air is basically a combination of dry air plus water vapor. So the amount of water vapor present in the air is known as moisture, and it is very important. And its quantity is very important for almost all the unit operation of food engineering. Next is dry bulb temperature. Next is dry bulb temperature. Dry bulb temperature. So do you know what is dry bulb temperature?
Yes, sir.
The actual temperature of moist air as measured by ordinary mercury thermometer is known as dry bulb temperature. Dry bulb temperature, or in short, you can say DBT. It is not affected by the. It is not. It is not affected by the humidity, moisture in air. Okay, so the dry bulb temperature is basically, in case of psychrometry, two types of temperature. Temperature is denoted in two terms. One is dry bulb temperature and wet bulb temperature. You must have studied earlier. So dry bulb temperature basically, in short forms, it is represented as DBT. Okay, that is dry bulb temperature. So the actual temperature of moisture as measured by ordinary mercury thermometer is known as dry bulb temperature. It is not affected by humidity or moisture in the air. How much amount of moisture or humidity is there in your air, that will not affect the dry bulb temperature. Mainly only the dry temperature is taken. So that means if you take a simple thermometer, if you take a, suppose a simple thermometer you have taken, okay, a simple thermometer, okay, so suppose this is a simple thermometer. So with the help of this simple thermometer, if you measure temperature, so that is known as dry bulb temperature. Okay, with the help of this simple thermometer, ordinary mercury thermometer, we know it is already available. So with the help of that thermometer, if we measure any temperature of the dry air, that will be dry bulb temperature. It will not consider this temperature will not say that how much amount of moisture is there in your air. This will simply say the dry bulb temperature. Okay, so the actual temperature of the moisture as measured by the ordinary mercury thermometer is known as dry bulb temperature, or DBT, and it is not affected or influenced by the humidity or moisture in air. Next is wet bulb temperature. Next is wet bulb temperature. What is wet bulb temperature? What is wet bulb temperature? What do you mean by wet bulb temperature?
So when cotton or some cloth is wrapped around the bulb with water, then the temperature when we take
It is
with the thermometer.
the temperature measured by the thermometer covered with wet cloth. Okay, so this particular thermometer, for example, if we take it, suppose we have taken this thermometer. Okay, let me copy it. This particular thermometer, for example, it is covered by a wet cloth. Okay, so suppose in water you have immersed that particular cloth and that is wet, so that cloth you are going to use here. Rather, we can change the color also. Oh, sorry. Suppose you have a wet cloth like this. So in thermometer, you have used one wet cloth. Okay, so you have used a wet cloth like this. So in that case, with the help of this thermometer, if you measure temperature, suppose this particular setup you are going to use for the measurement of temperature, so you will get a particular set of temperature after measuring, and that type of temperature is known as wet bulb temperature. And you will always observe that the wet bulb temperature is always less than dry bulb temperature. Wet bulb temperature is always less than the dry bulb temperature. So for representing thermodynamic property of air water vapor mixture, basically two types of temperatures are used. One is dry bulb temperature, that is only the dry temperature. With the help of a simple thermometer you are going to measure the temperature, that will not include the amount of moisture or humidity present in the air. So that is dry bulb. And wet bulb temperature is you are going to consider the humidity. Okay, that means for this reason, in the thermometer you will provide one wet cloth. You will cover it with the wet cloth, and with the help of that setup, if you measure the temperature of the air water vapor mixture or moist air, you will get the wet bulb temperature. And wet bulb temperature is always less than dry bulb temperature. Is it clear?
Yes, sir.
Yes, sir.
So how does it work? So you may ask me questions, sir. This wet bulb temperature, that's fine. Wet cloth is there, we provide it, and after that we get the temperature of air water vapor mixture. But why it is less than dry bulb temperature, and what is the mechanism for using or for getting wet bulb temperature? That is very important. Basically, psychrometer is available. In the psychrometer, two tips are there. One tip is for dry bulb temperature and one tip is for wet bulb temperature. If you directly provide the psychrometer in the system, it will give you two types of temperature, dry bulb and wet bulb temperature. But in wet bulb temperature measurement, what exactly happens? What phenomena exactly happens? That is very interesting. That should be known. So what happens, that I'm going to explain. Suppose let me copy this, move it further. Okay, like this. So in this one, suppose this is air, this is a particular system. Suppose let me provide it with some air particles. Suppose in a system, suppose in this system you have to insert this cyclometer. Okay, so in this system there is moist air, so that means there is unsaturated air. So when the unsaturated air flows through it, listen it carefully. When the unsaturated air, suppose this thermometer is here, it is a wet cloth. So when the unsaturated air flows through it, so what will happen? It is the air is unsaturated. Okay, so let me show you with the arrow. Suppose the unsaturated air is flowing through this. Suppose in a system you have inserted this particular type of temperature measuring device. That means you are covering the thermometer with a wet cloth, and you have inserted this particular instrument. So then suppose in the system there is unsaturated air. Okay, because normally in the atmosphere whatever air is there, it is not saturated, it is unsaturated. So if it flows, what will happen? Pressure difference, because in the wet cloth, so what will happen? Due to the pressure difference, there will be some amount of moisture transfer, in the unsaturated air. So as the unsaturated air flows, due to the initial vapor pressure difference between the wet cloth and the unsaturated air, there will be some mass transfer, or some amount of water will be evaporated from the wet cloth to the unsaturated air. So due to this reason, it tends to cool the liquid surface, the water surface, so that is on the wet cloth. Okay, due to this reason, as the heat is being, because initially the vapor pressure, due to the vapor pressure difference, the water gets evaporated. So when the water evaporation occurs, obviously some amount of heat will be involved. So as the some amount of heat will be involved, it will tend to cool down the surface of the wet cloth. Due to this reason, at the meantime, because it is cooled down, so some amount of sensible heat will be transferred from the dry air to the wet cloth. Okay, so that means two types of heat transfer is occurring in the system. One is sensible heat transfer, sensible heat transfer from air to water or wet cloth, and another is latent heat of water evaporation or heat transfer for mass transfer, that you can say. So latent heat of water evaporation from the wet surface. Okay, so that means on the wet surface, from wet surface. Yes, from wet surface, whatever. So two types of heat transfer: sensible heat transfer from the air to water, another is latent heat of water evaporation from wet surface. So at a steady state condition, these two heat transfer becomes equal. At a steady state condition, these two heat transfer becomes equal, and at that time the particular temperature of the water surface is known as wet bulb temperature. So as you give this thermometer covered with a wet cloth to the atmosphere, what will happen? The unsaturated air will flow, and there will be due to the pressure difference, initially some amount of moisture will transfer from the wet cloth or from the thermometer to the unsaturated air. So as a result, what will happen? It will tend to cool down the temperature of the wet surface. So finally, some amount of sensible heat will be applied from the air to the atmosphere. You can show the sensible heat like this. Some amount of sensible heat will be transferred like this. Some amount of sensible heat will be transferred from the air to the wet surface. So that means two types of heats are involved. That is sensible heat transfer from air to water. Another is latent heat of water evaporation. Okay. So under a steady state condition, these two types of heat transfer becomes equal, and at that condition, the particular temperature of the wet surface or water, okay, is known as, or the particular temperature of water surface becomes constant, and it is known as wet bulb temperature. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
So if you write down the definition again in a proper manner, so when stream of unsaturated air passed over a wet surface under adiabatic condition, evaporation of water takes place due to vapor pressure difference. The cooling effect produced by evaporation lowers the temperature of water surface. The temperature differences, hence the temperature differences between air and water surface transfers sensible heat from the air to water which supplies latent heat necessary for evaporation. Under a steady state condition, these two types of heat becomes equal. In this situation, the temperature of water surface becomes constant, and this is known as wet bulb temperature. Is it clear? When a stream of unsaturated air passed over a wet surface, so this is the wet surface, passed over a wet surface under adiabatic condition. Adiabatic condition should be mentioned. That means there will not be any heat transfer from the outside or inside. Okay. Evaporation of water takes place due to vapor pressure difference. The cooling effect, because the evaporation takes place, there will be some coolness. Okay, cooling of the liquid surface. So the cooling effect produced by evaporation lowers the temperature of water surface. As a result, what will happen? Because lowers down, so there is some sensible heat in the air that is flowing. So hence the temperature difference between air and water surface transfers the sensible heat from the air to water, which supplies latent heat necessary for evaporation. Okay, so because for evaporation of moisture that is coming from water surface to the air, some amount of latent heat is necessary. So that latent heat is basically supplied by the sensible heat that is being transferred from air to water. So under a certain condition, under a steady state condition, these two types of heat, one is sensible heat transfer from air to water surface, and then latent heat necessary for the water evaporation from the wet surface. So these two heat becomes equal. So at that condition, the particular temperature of the water surface is constant and is known as wet bulb temperature. Is it clear?
Yes, sir.
Yes, sir.
So next we will study after this next is dew point temperature. So what is dew point temperature? It is also very, very important. So as I have said, dew point temperature, dew point temperature. So it is the temperature, rather we can say, when an air water vapor mixture, or we can say moist air, is cooled at constant pressure constant humidity. This is also known as sensible cooling. Sensible cooling. So when a air water vapor mixture or moisture is cooled at constant pressure or constant humidity, or known as sensibly cooled, a temperature is reached. A temperature is reached when mixture becomes saturated. That means 100% relative humidity. Saturated. Saturated. Further, lowering the temperature results in condensation of moisture. Condensation of moisture and making foggy environment. So this particular temperature is known as dew point temperature, or it is known as DPT. So that means, in a system, suppose you have a water vapor mixture and you are sensibly cooling that water vapor mixture. So that means you are cooling, suppose in a system, in a house, in a room, there is air water vapor mixture or moisture. So, and you have cooled down that moisture at constant pressure, at constant humidity, or rather you can say it is sensibly cooled. So a temperature is reached where or when the mixture becomes saturated. Saturated means 100% relative humidity. So further lowering the temperature, so beyond dew point, if you decrease or further lowering the temperature beyond dew point, in that case, there will be condensation of moisture and making foggy environment. Okay, in the winter also you have seen why fog is created, because it goes that the temperature of the atmosphere goes below dew point temperature. So if it goes below dew point temperature, there will be moisture, the fog will be developed. You can observe foggy environment because the temperature of the atmosphere has gone below dew point temperature. Okay, so that means when a water vapor mixture is sensibly cooled or cooled with constant humidity and constant pressure, so a temperature is reached when the mixture becomes fully saturated. Okay, and if you go below that temperature, in that case there will be condensation of moisture and fog will be created. Okay, you may observe foggy environment of the atmosphere. So this particular temperature is known as dew point temperature. It is represented by dPT. Okay, and one more thing, at 100% relative humidity, this is a very good question. At 100% relative humidity, all three temperatures are equal. All three temperatures are equal. What are the three temperatures? Can you tell?
Dry bulb, wet bulb, and dew point.
Dry bulb, well bulb, and dew point temperatures. They will be equal. Okay. So this is all about dew point temperatures. Next is specific humidity. Next is specific humidity or humidity ratio or absolute humidity. Specific humidity or absolute humidity ratio. Okay, so how will you define it? How will you define it? It is defined as amount of moisture or water vapor. Rather, you can say amount of water vapor present per kg of dry air. Okay, so if you have a 1 kg dry air, in 1 kg dry air, how much amount of water vapor is present is known as specific humidity or absolute humidity or humidity ratio. So it is represented, so it is given by capital H, it is given by capital H, it is equal to 0.622 divided by into 0.622 into capital small pb, rather even write down pb or pw, okay, divided by divided by okay, so specific humidity or humidity ratio is amount of water vapor present per kg of dry air, and if we represent it by S, H is equal to 0.62 into PW divided by P minus PW. Here H stands for absolute humidity and capital PW. In different book you can get different denotation for partial pressure, but here we are denoting as PW is equal to partial pressure of water vapor. Okay, and capital P equal to total pressure. Total pressure of the air, moisture of the moist air or air water vapor mixture, rather you can say, and capital H equal to specific humidity or absolute humidity or humidity ratio. Okay, is it clear? Is it clear?
Yes, sir.
Yes, sir.
So next is saturated humidity. Okay. One second. Okay. So for saturated air, so if you have a saturated air, for saturated air, is specific humidity. For saturated air, specific humidity is represented as capital HS. Okay, for specific humidity, suppose the humidity that we have shown here, this is for normal air. But if you have a saturated air, in that case, if you have a saturated air, for saturated air, specific humidity is represented as HS. In that case, it will be presented as HS. Okay, and what will be the expression? What will be the expression for that? HS will be equal to similar 0.622 into, here it will be capital PS, partial pressure of saturated air. Okay, partial pressure corresponding to saturated air. Okay, partial pressure of saturated air. PS divided by capital P minus PS. Okay, so PS stands for partial pressure of water vapor when it becomes saturated under the same condition, same temperature. Okay, suppose PW was partial pressure of water vapor and PS stands for partial pressure of saturated air. Okay, partial pressure of saturated air. Okay, so the same air, when it suppose at a particular temperature you have this specific humidity value. Okay, so under the same condition, if it becomes saturated, in that case, you can determine with the value of this. So for saturated air, the specific humidity represented as HS. It is also known as saturated humidity. It is also known as saturated humidity, and it is equal to 0.622 into PS divided by P minus PS. PS stands for partial pressure of saturated air. Okay, or partial pressure of moist air when it becomes saturated under the same condition. Okay, so that you can say. Next is relative humidity. Next is relative humidity. Next we can write down relative humidity. So it is defined as the as the partial pressure of water vapor and partial pressure of water vapor present in air and partial pressure of water vapor when it becomes saturated, or you can say saturation vapor pressure, or you can say saturation vapor pressure. So it is defined as the partial pressure of water vapor present in air and partial pressure of water vapor when it becomes saturated. Partial pressure of water vapor when it becomes saturated. Okay, under same temperature and atmospheric pressure. It is represented by phi. Okay, so you can write down RH also. So most of the time people use RH equal to this much, phi or RH, whatever you want to write. So it is defined as the partial pressure of water vapor present in air and partial pressure of water vapor of the same air when it becomes saturated. Here you can write down of the same air when it becomes saturated. Okay, so it is defined as the partial pressure of water vapor present in air and partial pressure of water vapor of the same air. Here you can write down of the same air. Of the same air. Of the same air. Okay, so it is defined as the partial pressure of water vapor present in air and partial pressure of water vapor of the same air when it becomes saturated, or rather you can say saturation vapor pressure under same temperature and atmospheric pressure. It is represented by phi or RH. Okay, so your RH will be basically PW by P S into RH in percent I'm writing down, RH in percent. This one. Is it clear? Is it clear?
Yes, sir.
The next, degree of saturation. Saturation. Degree of saturation. It is also known as mu. Okay, degree of saturation is basically equal to, defined as capital H divided by HS into 100. Not 100. There should be English 2. Okay, so that means degree of saturation, it is also known as mu. Okay, so it is given by this, that is H stands for what? H stands for saturation humidity, specific humidity. Okay, and HS stands for this saturation humidity. So if you take ratio of this, if you take ratio of this H by HS, it will give you degree of saturation. Okay, or if you need to find out percentage saturation, you will multiply it with 100. Next is enthalpy, enthalpy of moisture. Next is enthalpy, enthalpy of moist air. So what is enthalpy of moisture? Can anyone tell? So it is defined as total heat in an air water vapor mixture. This includes both sensible and latent heat. So in a air, whatever air you have, moisture you have, that means a composition of or a mixture of air, water, vapor. So for that air, the total heat is represented by enthalpy. So that total heat or enthalpy is basically equal to sensible heat and latent heat of the air, water, vapor mixture. So enthalpy is basically sensible heat plus latent heat of the air water vapor mixture. Air water vapor mixture. So in terms, if we write down, so this enthalpy, it is represented as small h. It is represented as small h. We can write down as CS, or rather you can write down 1.005, or rather short form, we will discuss it afterward also. The short form CS into capital T minus 0 plus lambda. Lambda I'm writing down, you can write down in terms, I'm writing down like this. Lambda capital H, that is enthalpy. So lambda we can write down here. Lambda. So here CS stands for H, this small s is enthalpy, and CS stands for humid heat. CS stands for humid heat, and T is the temperature. Okay, temperature, and lambda stands for what? Latent heat, and H is humidity. So for a particular air, if you need to find out enthalpy, first of all you need the temperature of the air, at what temperature the air is. Secondly, you need the latent heat of the air at that particular temperature. Then you need the amount of humidity present in that air at the particular temperature, and you need humidity. So if you combine it, then you can get the total enthalpy. Okay, so next we will see what is humid heat, because we have used humid heat here. So what do you mean by humid heat? So humid heat, very simple, it is similar to specific heat only. Humid humid heat, it's similar to specific heat only. So simply this is simply heat capacity of moist air. It is defined as amount of heat necessary to raise temperature of 1 kg moist air by 1 degree Celsius. So in case of moisture, you can write down air and water vapor mixture, whatever you want. So it is the amount of heat necessary to raise the temperature of 1 kg moisture or 1 kg dry air and is accompanying water vapor by 1 degree Celsius. And it is given by CS. Remember, here we have used for the enthalpy, we have used CS. So this CS equal to CS, that is humid heat, is equal to 1.005 plus 1.88 capital H kilojoule per kg dry kilojoule per kg dry air. Is it clear? Is it clear? Students, any confusion you have? So next is humid volume. Humid volume. So humid volume, it is the volume of 1 kg dry air and is accompanying water vapor under a given temperature and pressure. Under a given temperature and pressure. Okay, so under a given temperature and pressure, the amount of volume, the volume occupied by 1 kg of dry air and is accompanying water vapor is known as humid volume. So it is represented by VH. Its unit is in meter cube per kg. Equal to, you can write down like this, is VH equal to 0.00283 plus 0.00456 capital H into P plus 273. So its unit was, what is its unit? Its unit is meter cube per kg. Meter cube per kg. Is it clear? This is all about humid volume. Next is psychrometry chart. We will see what is psychrometry chart. Do you know psychrometry chart?
No, sir.
So next we will see psychrometry chart. 1 second. Wait 1 second. I'm giving chart. Wait 1 second. We are getting the graph of this. So do you know psychrometric chart? This is a psychrometric chart. In this chart, this particular section is known as dry bulb temperature. So in the psychrometric chart, if you observe here, you will get dry bulb temperature, and in this one you will get humidity ratio or specific humidity. Okay, and this blue line here you will get the wet bulb temperature. This blue line, if you suppose some condition is here and if you go along the blue line, so you will get the wet bulb temperature. These are the wet bulb scales. Okay, and these green lines, these lines are representing relative humidity. Okay, so these are the important terms. And then enthalpy is also represented. If you watch here, enthalpy can be represented by here also. So the wet bulb temperature line, and this is enthalpy. Here you can get the enthalpy also. So in this psychrometric chart, this horizontal one you will get the dry bulb temperature, and the wet bulb temperature you will get here. Okay, so this blue line, if you go, you will get the wet bulb temperature, and this side, this is known as humidity ratio or specific humidity, and these green lines are representing relative humidity of the system. Okay, so these are the important terminologies. So if you have the psychrometric chart, you can easily determine the properties of air water vapor mixture or thermodynamic property of air water vapor mix. Psychrometry. So let us write the first problem. The ambient temperature, the ambient air, the ambient air, reduce the font size. The ambient air at 50 degrees Celsius, at 50 degree Celsius, dBT, drivable temperature, as 15% relative humidity at atmospheric pressure. At atmospheric pressure. Find out rather we can say find out. First one we need to find out partial pressure of water vapor, we are writing as PW, and we need to find out relative humidity RH and specific humidity H, humidity ratio, and degree of saturation, degree of saturation, enthalpy of moisture, enthalpy of moist air, then humid volume and humid volume. Okay, so these things we need to find out. So for this we'll follow psychrometry. This psychrometry chart, as you can see. So first of all, the ambient air at 50 degrees Celsius dBT has 15% relative humidity. So ambient air is at 50 degrees Celsius, right? So this is 50 degrees Celsius, this one, and relative humidity is 15%. That is in between this. So we can make a plot here. So our temperature is 50 degrees Celsius. This is drive out temperature. So 50 degrees Celsius will be somewhere here. 46, 47, 48, 40, 10. So this one will be 50. Okay. This will be somewhere here. So this point, okay, this point is 15%. So this is 50% dBT. This is 50% dBT, and so this is 50% dBT. This is dBT. We know that this is basically dBT, D, B, and T, type of temperature. So our temperature in the question is 50 degrees Celsius. Is 50 degrees Celsius. So here this is 50 degrees Celsius and 15% relative humidity. So we'll draw the line like this, and 50% relative humidity is here. So this is the point. So this is the point. So in this point, the specific humidity is how much? This one, that is 0.012 kg water vapor per kg dry air. So we can find out from this our, let me write down. So from this you can write down our H value is how much. From this you can say 0.012, as we have seen here, 0.012. Okay, 0.012. So this is the point that we have allocated. So under this point, the humidity we can see, that is, if you go straight, you will get 0.012. So 0.012 kg water vapor per kg dry air. Kg water vapor per kg dry air. So if H is this much, then we can find out, we know that capital H equal to 0.622 into third bracket Pw, partial pressure of water vapor, divided by capital P minus Pw, that we know. If we put the value here, so total air we are taking, total pressure we are taking 1.013, 101.3. Let us take the conversion. 101.3 kilopascal or 101.3 kilopascal total pressure we will going to take. So if we put here, so H value we have determined already, 0.012 equal to 0.622 into, we can give Pw divided by capital P minus capital P, we are giving 101.3 kilopascal or 1.013 we can use. It's up to us, 1.013, that is in bar. Okay, minus, here it will be division, minus Pw. Okay, so if we calculate here, what we can get, if we calculate here, so it will be here 0.012 into 1.013 minus 0.012 into Pw. So that you can see. So this is equal to 0.622 into Pw. Pw you can write like this. So now Pw will be how much? So if we calculate here, Pw will be, you can get the value, it will be 0.012 into 1.013 equal to 0.0121, 0.0121 equal to, so it will be 0.622 Pw plus 0.012, 0.634, 0.634 Pw. Hence Pw will be, Pw will be 0.0121 divided by 0.634. So we are getting 0.01. That means 0.1 you are getting. We are getting 0.1. 0.1 bar. We are getting 0.1 bar. Okay, so 0.1 bar we are getting here. So from this, if we calculate further, so PW we know. So now we need PW. We have calculated already the first one. Relative humidity is how much? PW by PS, right? PW by PS. So we need the value of PS. So PS, how can you calculate? We have the relative humidity value already. It is 15%. It is given in the question. Okay, it is 15% already. So if we write down further, here it will be relative humidity. Relative humidity will be PW by PS into 100, that we know. So 15% you are writing here, and PW is 0.1 bar. PW is 0.1. Okay, so here it will be replace here 0.1 divided by PS into 100. So if you write it further, it will be uh, this will go there. So divided by 15 into 100. 15 into 100 equal to PS. So the value of PS will be, if we calculate here, it will be so 0.1 divided by 1500. One second. We are getting 0.1 bar. We are getting 0.1 bar. So here it will be here it will be how much? This will be 0.01. 0.01. Okay, 0.01. So 0.15 into 0.1 it will give you 0.015. Rather, we can write down 0.15 bar. So you have calculated the value of PS. We know the value of PS. Now we can calculate H is already we have calculated. So degree of saturation we need to calculate. So for degree of saturation, what value we need? For degree of saturation, we need what value? We need uh, you know H divided by HS will give you the degree of saturation, because we know that degree of saturation. Let me reduce the font size. So degree of saturation DS, degree of saturation DS equal to is basically H by HS. So H value we have already calculated. It is 0.012. It is 0.012. Okay, so we need the value of HS. So HS will be how much? HS will be how much? HS, this one basically it will be 0.622 into PV into third bracket PV divided by capital P minus PS. So that is saturation partial pressure of saturated air. Okay. Okay, so this we know. So the saturated value we have calculated that PS equal to 0.015 bar. So if we put this value here, we can get that get the value of saturation humidity, that is HS equal to HS value we will get 0.08 0.086 kg water per kg of water vapor that we can get. And once we have this value HS, so H value already we have calculated from the chart, that is 0.012. So 0.012 divided by 0.086 will give you degree of saturation. And enthalpy we know already. Enthalpy is, what is the formula? The formula for enthalpy is, let me write down it. Enthalpy, it is also written as small h is equal to 1.005 plus 1.88 capital H, okay, and into capital T, that is the temperature, or 0 minus 0 plus lambda H. So lambda is 2500 for this particular condition. For this particular lambda, you can write down lambda into H. So I know. So for this particular condition, H value is already, you know, H value is how much? H value we have calculated from the psychrometric chart. H value is 0.012 kg water vapor per kg dry air. Okay, so this value we can put here in place of H, and in place of T we will put 50 degree. 50 degree is given in our question. This 50 degree will put here. Okay, so 50 minus 0. Okay, and then lambda is how much? Lambda is, for this case, is from the standard chart we can get, that is 2500. Okay, so 2500 into this one 0.012 will give you the value of impulse. So the H value we can put here. T is already given 50 degrees Celsius and lambda is 2500. We will use 2500. If you write down here, so it will be 1.005 plus 1.88 plus 1.88 H. H is how much? 0.012. Okay, now we can close the bracket, and then here it will be into 50 minus 0 plus 2500. This is for this condition the lambda value, and 0.012. So if we calculate on the basis of this, we can obtain the value. So the value of enthalpy will be how much? 78.78 kilojoule per kg dry air. So that we know. So next is humid volume. Humid volume, how to calculate? Humid volume is, we know that is basically represented as VH. Okay, V capital H, you can write down like this, equal to 0.00283 plus 0.00456 into H into P plus 273. P plus 273. Okay, so wait one second. Okay, so T plus 273. So in this formula, if we put this will be VH actually, VH VH like this. Okay, so this VH, that is humid volume, can be calculated with the basis of this equation we have already discussed. So the value of H, that is 0.012, we can put here, and temperature is 50 degrees Celsius. So 50 plus 273 will give the value of VH, that is humid volume. So in this way, all the required things we have calculated. So we'll solve the next problem. We'll solve the next problem. So next problem is the humidity ratio of atmospheric air at 25 degrees Celsius. The humidity air so the humidity ratio of next problem the humidity ratio the humidity ratio of, so you know that humidity ratio and specific humidity, they are saying the humidity ratio of atmospheric air at 25 degrees C dBT, drive up temperature, has is 0.012 kg water vapor per kg dry air. Determine partial pressure of water vapor, then dew point temperature dpt, and relative humidity, then degree of saturation, okay, degree of saturation, and then enthalpy. So what we need, first of all, what is given, 25 degrees Celsius dBT and 0.012 kg water vapor and kg dry air. So we'll go to the psychrometry, that 25 degrees Celsius dBT. So this is dBT. So this is basically dBT. This is dBT, we can say. This is dBT. Okay. This is dBT, and this is what? This is our H value. This is our H value. So 25 degrees Celsius dBT and 0.012 humid ratio. So if we plot here, you can get 0.012 and 25 degrees Celsius. So the point will be somewhere here. Okay, and it will be like this. Okay, so our required point is this one. Our required point is this one. Okay, so required point is this one. From this, we can calculate the required values. So first of all, what do we need? We need first of all PW value. So H value is already given 0.012. If we have the H value, we can easily calculate the value of PW, that is partial pressure of water vapor, because we know that this H, that is humidity ratio or specific humidity, is 0.622 into earth bracket PW divided by capital P minus PW minus PW. So if we put here PW values, we need to calculate. The H value is already given. If we put 0.012 here and capital P equal to, if we are putting the total pressure in bar 1.013 bar, so then we can get the value of, like the previous problem, we can get the value of PW equal to how much? 0.019 bar. Okay, so the first one you have calculated, and relative humidity you can get here also. Suppose from the psychrometry, so see the point, this is the point, so this is the point. Okay, this is the point, this is the point. If you see, this is 50, this is 60, so this is the humidity line. These lines are 50%, 60%, 70%, 80%. These are humidity lines, relative humidity lines. 40%, 50%, 60%. So if you go along the line, you can see I am giving it separate color. If we come along the line, see like this, so it is connecting 60% relative humidity. So our relative humidity is how much? Relative humidity is, so what we need to calculate? So first and third we have calculated, and then we need DS, that degree of saturation. Okay, so for degree of saturation we know that DS equal to capital H by, that is humidity ratio or humidity ratio or specific humidity or absolute humidity divided by saturation humidity, that is HS. Okay, so that we need. So H value already we have, it is given 0.012, but HS we don't have. For this we'll be using this equation. So 60% relative humidity we know, 60% relative humidity. If we have 60% relative humidity, 60 will be equal to this PW we know, 0.019 divided by PS into 100. So it will be how much? It will be how much? PS will be equal to 0.019 divided by 0.6. The value will be how much? Let me calculate it. So 0.019 wait one second, 0.019 divided by 0.6, so it is giving 0.031. It's giving 0.031. So PS equal to 0.031 bar. Okay, so once you have the value of PS, we can calculate the HS, because we know that HS equal to 0.622 into saturation pressure divided by capital P minus PS third bracket close. So we have the value of 0.031. 0.031 you can put, and total pressure is how much? 1.013 bar. So we can get the value of HS. So the value of HS will be how much? The value of Hs will be 0.02 0.02 kg water vapor per kg dry air. So once we have these values, this Hs value we have, H value we have, if we put here, we can get the value of ds, degree of saturation. And enthalpy also we can easily calculate, because enthalpy we know, uh, enthalpy is how much? Enthalpy value we know, we have calculated in the previous problem. Just we need to put the value of capital T. The temperature is already given 25, and enthalpy is 2500. Okay, the value for the latent heat lambda value. Okay, and H value we have already, it is given. So from that we can easily calculate by putting in the formula. But the problem is dpt. How to determine the uh, dew point temperature? It is very important. So for this, what we will do, dew point temperature is always obtained by sensibly cooling. So the point is, if you check in this graph, the point is here. So we need to make sensible cooling. Sensible cooling means in a psychrometric chart, suppose you have a psychrometric chart like this. This is psychrometric chart. So you need to cool like this. Okay, cool like this in the parallel manner like this. So this will be sensible cooling. This will be sensible cooling. So if you go here, let me take a straight line. We'll go like this and we'll go up to 100% humidity like this. Okay, and once again, this is not straight. This is not straight. Let me put a final line. Yeah, this one. So then if you go further, so this temperature, this particular temperature, so this temperature will show dew. So this is how much? 15, 16, 17. So this particular point will give you dpt. So your dew point temperature, that is dpt, you can write down dpt equal to how much? 17 degrees Celsius. 17 degree Celsius. So it is always obtained by sensibly cooling. Okay, so that means from the point, this is the point of the current atmosphere, of the current condition of the atmospheric air. If we go for sensibly cooling, we'll go this side in a parallel manner, because if you go, see, if you go through this green line, that is the straight line, constant line, so you can see this humidity is constant. There is no change in humidity. If you remember the definition of dew point, if you reduce the temperature with at constant humidity and constant pressure, or if you sensibly cool the particular condition, then we can reach the dew point temperature. And after reaching here, this is 100% relative humidity line, this one. So this particular line is 100% relative humidity line, this line. So this point is reached here, that means you have reached 100% relative humidity, saturated condition. So under this condition, the respective dry bulb temperature is known as dpt. Okay, dew point temperature. So this is all about this problem. So with this, we are finishing our